Hello everyone, my name is Farzad Jafar Kazimi. I'm an Associate Professor of Mechanical Engineering at Azad University, Islamic Azad University, South Tehran branch. This is the Advanced Fluid Mechanics course, the first session, which is for international students. Our international students are from Iraq and Afghanistan. To know more about me, I invite you to have a look at my Google Scholar profile or join me in LinkedIn. Today we want to speak about some introductory aspects of fluid mechanics. Then we will continue in more detail in the next sessions. The history of fluid mechanics goes back to Archimedes, and you can see here a lot of famous names. You may heard about them, like Newton, Leibniz, Bernoulli, Euler, Navier, Stokes, Reynolds, Prandtl, Taylor, and many others who did a lot of work about fluid mechanics, among other topics of science. You may know about them by googling them into the web, and it's also good to know the history of any lesson you learn, and fluid mechanics is not an exception. What's fluid mechanics? Fluid mechanics is a branch of science that deals with the study of fluids. What's fluid? Fluid is a liquid or a gas. The liquid or the gas, which we name them fluid, may be in a state of rest or motion. It's an important subject in some areas like civil, mechanical, and chemical engineering. And there are three main branches of fluid mechanics, which are fluid statics, fluid kinematics, and fluid dynamics. Fluid mechanics branches may be written as you can see here. These are not the only subdisciplines, but the most important ones. For example, aerodynamics, which deals with the motion of air and other gases and their interaction with bodies, such as lift and drag of an airfoil or a wing of an aircraft. Hydraulics, which discuss about the application of fluid mechanics to engineering devices, involving liquids such as flow through pipes and open channels and something like this. Geophysical fluid dynamics, which is associated with the dynamics of the atmosphere and oceans and weather systems. And finally, biofluid mechanics, which is approximately a new topic and very important one, and a lot of progress you will see in the future about biofluid mechanics. The first thing to discuss, and I want you to learn it, is the difference between solids and fluids. As you can see here, a solid can resist an applied shear stress by deforming. It means that when you apply stress on a solid body, it will be deformed. A fluid also deforms, as you can see, but there's a difference which I underlined here, and that's the word of continuously. You cannot see this word for the solid. So a fluid will also deform, but continuously under the influence of a shear stress. And the next important phrase is that no matter how small. Again, you have not such a phrase for the solids, but here in fluids you should write it. No matter how small, a fluid will deform continuously under the influence of a shear stress. The next thing is that in solids, the stress is proportional to a strain. You can see in the right picture, which is the Hooke's law. You know that in the elastic region there's a linear relationship between a stress and a strain. And for the fluids, the proportionality is not like the solids, and as you can see here, in fluids stress is proportional to the shear rate, as you can see in the picture. And the interesting point here is that the form of the proportionality between shear stress and the shear rate is dependent on the type of fluid, as we'll discuss more in detail later. You can see here the difference, the first difference we discussed, in a graphical form, which may help you to understand it better. When a constant shear force is applied, a solid eventually stops deforming at some fixed strain angle, as you can see in the top picture. In the top side here, there's a solid under a shear stress tau, as you can see, and this is the time zero when the stress is starting to be applied and will be remained further on. You can see that at time t1, for example, the shape of the solid body will be, as you can see here, and the same shape will be existed for time t2 also, and there is no difference between t1 and t2 in the shape of the solid body. But for the fluid, as you can see here, a fluid never stops deforming and approaches a constant rate of strain. Actually, instead of saying it approaches a constant, for example, strain, you shall say it approaches a constant rate of strain. So as you can see in the below picture at here, a fluid under the same shear stress, as you can see, will never stop deforming, and that's an important difference between solids and fluids. We want to have some first to have a short review on the branches of fluid mechanics, and then we classify the flow in different forms. Fluid statics is a branch of fluid mechanics, as I discussed before, and generally the fluid statics is discuss about the fluid which is at rest. The fluid may be either a liquid or a gas. So the fluid which is in a state of rest is called as static fluid, and its study is called as fluid statics. There is an exception here, an interesting exception here is that, and it is the rigid body motion. You can see here two examples of a rigid body motion. In the left you can see a linear rigid body motion, and in the right side you can see rotational motion of a rigid body, or as a rigid body. If you move here in the left a body of a mass of liquid, as you can see here, at a constant acceleration a, for example, to the right, like you can see here for the truck shown here, either in a horizontal surface road or in a sloped road. There is no difference actually in the basics. And as you can see here, the surface of the fluid will not be in a horizontal position, and it will take an angle theta, as you can see here. But the important point here is that after passing the unsteady state, the form of the surface, of the free surface, then will remain constant at the angle shown, and then the mass of the liquid behaves like a solid. So if you want, for example, to calculate the pressure here at this point, it will be rho g at the height multiplied by the height of liquid here. Or if you want to, for example, calculate the pressure here, again you can use the Pascal law to calculate the pressure. Another form of rigid body motion which is categorized in the fluid statics is the rotational motion. For example, you can consider a cylinder like the one shown here, which can be rotated either around its own axis or another axis of rotation. Actually, there is no difference in the basics, but the shape of the surface will be certainly different in these two cases. By the way, if you rotate a cylinder like shown here about its own axis, as you can see, the form of the surface will be like a parabola, and again here the fluid in the cylinder behaves like a solid, and you can use the equations which are used for the static or fluid static for these two cases shown in this slide. These are named rigid body motion. So rigid body motion is also a special case of fluid statics. There's an exercise here for you. Fluid statics means non-zero normal and shear stress, means zero negative normal stress and zero shear stress, means non-zero normal stress and zero shear stress, and zero normal stress and non-zero shear stress. You can stop the video here and think about the correct answer, and again when you have an answer, then you can replay the video. What do you think? Which one is correct? Okay, here is the answer. Answer C. A fluid at rest is at a state of zero shear stress. So in the fluid at rest, or static or fluid statics, the normal stress is there and is not zero, but the shear stress is zero. You can see here a picture in the right which shows an element of fluid surface, or the forces acting on an area of the fluid, and as you can see, the force F can be divided to its components. As you can see, the component tangent to the surface, Ft, and the component normal to the surface, Fn. This says that for the fluid at rest or fluid statics, you have only the normal force here shown here, or normal to the surface, Fn, and the shear stress, Ft, is zero. So for a fluid at rest, the forces are always normal to the surface, because if it has an angle like this, then it should have a tangential component, but there is no tangential component. So the only force, or the force, is only in the normal direction. So in the fluid at rest, shear stress is zero and you have only normal stress. The second branch of fluid mechanics is fluid kinematics. The fluid which is in a state of motion is called as moving fluid. The study of moving fluid without considering the effect of external pressure or forces is called fluid kinematics. So in fluid kinematics, you consider the fluid motion, but do not pay attention to the reason of the flow, which may be pressures or forces. If you want to consider the forces or pressure acting on the fluid, then that's another branch of fluid mechanics which is named fluid dynamics. As you can see, the branch of science which studies the effect of all pressures, including the external pressure on the moving fluid, is called as fluid dynamic. I think it may be better to say the branch of fluid mechanics which studies the effect of all pressures and so is called fluid dynamics. What are the applications for the course we are discussing of fluid mechanics? Tell it frankly, fluid mechanics has many applications in many areas, and it's really an important course for you to learn. You can see here some of the application, and there are much more to say. So it's a really important topic, and maybe the simplest one is its application in convection heat transfer. For example, you have another course, maybe with me or another professor, about convection heat transfer, and then you can see in that course that in order to calculate the temperature distribution in a fluid, you need the velocity components to be calculated first, or if the flow is coupled like the natural convection, then you should solve all the equations together, the equations for the flow and the equations for the energy. So it is a really important topic. In what follows, I want to have a review on classifications of flow phenomena. It's a really important thing to learn, and we want to have a short review on some of them. For some of them we will discuss more in the course later, but today I want to have a short review on the different types of classification which we will generally have in fluid mechanics. You can see here the list, and let's start. The first is internal versus external flow. Internal flow is a flow that is bounded by what? By boundaries. What are the boundaries? The boundaries may be a pipe, a channel, or something like this, as you can see here in the left. For example, the flow in a pipe is called internal flow. But as you can see in the right side, for the external flow, the outer boundary is actually infinity. The flow over, for example, an airfoil, the flow over a chimney, the flow over a car, the flow over a missile, the flow over a turbine blade, and many others can be named as external flow. It's very important when you are going to solve a fluid mechanic problem, first ask yourself, is this flow an internal or external flow? Why? Because there are a lot of different definitions for the internal versus external flow. Same applies, for example, in the heat transfer, convection heat transfer. You can see later that the equations which are used in the external flow are completely different with the ones which are used for the internal flow. There is an exception here for the free shear flow. What's free shear flow? The best example of free shear flow or jet flow is the one I've shown here. For example, the flow which is exiting a nozzle, as you can see here. Exiting from a nozzle into a stationary fluid. Suppose that the fluid here is stationary at first, and suddenly a jet of fluid enters the stationary fluid. Actually, you cannot define this flow either as an internal or external flow because there is no boundaries. This type of flow is called free shear flow, and it has a lot of applications in fluid mechanics and also in heat transfer, but it's outside the scope of this course, and if you are interested, I refer you to the more advanced books on fluid mechanics, or you may search it in the internet. The next classification of flow, which is very important for you to consider or distinguish, is pressurized flow versus gravity flow. As you can see, flow under pressure, example liquid flowing in pipes with pressure, are generally driven by, for example, a pump or fan or something like this. In this case, driving force for the flow is pressure and gravity. It means that in addition to the gravity, you have another form of driving force. For example, like the pump shown here in the right. In the right, you can see, for example, a pump which is used to pump water from the this surface. For example, this may be a vessel or something like this to an upper height. The other form of flow is the flow due to gravity. In this case, the driving force is generally only gravity. You can see here an example. For example, an elevated tank here at an elevation of, for example, 750 feet, which is used to supply water to a town here at a lower elevation. There may be also some distance here and also a height difference. Generally, most of the flows we encounter in fluid mechanics are of this type, the flow under pressure or pressurized flow. But there are a lot of applications also for the gravity type of flow, like the one shown here. In pressurized flow, as you can see here in the top picture, the pressure generally decreases along pipe length. There are exceptions also where the pressure may be decreased. We will discuss them later. But generally the pressure will be decreased. For example, if the pipe diameter is constant, as you can see here, from 1 to 2, then pressure at point 2 which will be less than the pressure at point 1. While in gravity flow, as you can see here in this picture here, pressure at the surface is equal to the atmospheric pressure. And if you are considering the pressure as gauge pressure, then you can see that the pressure at the free surface is 0. An example is, for example, open channel flow, like the one shown here. There are two types of gravity flows actually. The first is open channel flow, like the one shown here in the left, and the first is the flow in a pipe, but partially filled pipe. It's very important to understand this, because if the flow is in the pipe is full and under pressure, then it will be categorized as pressurized flow. But if the flow is in the pipe but it is not full and under pressure, like the one shown here in the right, then it is a partially filled pipe, and the driving force for this type of flow is again gravity. So if the flow is partially filled in a pipe, the pressure at the surface again will be 0, or atmospheric pressure. It may be interesting for you because one of my own expertises is on flow measurement, and I am very interested to show you examples of the fluid mechanics application in flow measurement. It's an interesting topic in fluid mechanics. For example, there are a lot of devices which are used to measure the flow in the pipes. This is an electromagnetic flow meter shown here in this picture, and you can see that if your pipe, like the one shown here, is partially filled, then you should consider this when selecting a flow meter. And if you do not pay attention or consider this, then the flow meter may read wrong. So this is a very important topic to consider. Okay, going to the next classification. The next one is classifying the flow into steady or unsteady flow. In a steady flow, fluid parameters are velocity, density, pressure, acceleration, and so on. At a point does not change or do not change with time. So round of any quantity with respect to time is 0. You can say d, but I'm afraid if that property may depend on other parameters in addition to t, so it's safe to say round of that parameter to round t is equal to 0. While in unsteady flow, fluid parameters such as velocity, density, and others at a point change with time. So you can see that in the second one, you can say that round over round t is not equal to 0. These are examples. For example, a startup process. A startup process. What does mean a startup process? For example, when you start a pump, when you start a fan. You can see the same when you shut down that device, for example, shut off a valve or something like this. Many examples can be given from everyday life. Water flow out of a tap which has just been opened. Yeah, this is again an unsteady flow. This flow is unsteady to start with, but with time does become steady. Again, an exercise for you here. What do you think? Is this a steady or unsteady flow? You can stop the video and think about that. What about this? Is this a steady or unsteady flow? In this case, there is an inlet to the tank which is equal to the outlet flow rate, but in the in this picture there is no inlet. What do you think? I think you are right, because in this case, the first case, as the height will be decreased, so the flow velocity at the outlet will also be decreased, because the flow velocity here depends on the height of the tank. But if the inlet flow rate is equal to the outlet flow rate, then the height will remain constant, and if the height remains constant, then the flow velocity here at the exit will be also constant. So in this case, the flow will be steady. Some flows, such as the wake behind the bluff body, is always unsteady. Always unsteady. It's very important. Actually, you cannot take the flow behind the bluff body, like for example a cylinder like this, as steady at no time. This is named vortex shedding behind the bluff body. It has a lot of application also in fluid mechanics, and also in my interested topic, flow measurement. There are some type of flow measurement devices like named vortex flow meter. We may discuss about them later. So in some flows, the flow is always unsteady. So there is no time that you can say that, okay, after passing this time the flow will be steady. No. This is another example for the unsteady flow. For example, water hammer. Water hammer is a bad situation actually, a bad thing in pipe flows, liquid flows. Actually, there is a water hammer also in steam flow, but that's different. We may discuss about that later. Suppose, for example, the flow in a pipe when the valve here is closed, so there is no flow in the pipe. Now, suppose that the valve is fully open, then the flow will be here. Now, if you shut the valve or close the valve suddenly, then there may be an unsteady process named water hammer. Water hammer produces very high positive or negative pressure in the pipe, and as you can see here in the right, it may damage the pipe. It's an interesting topic also in fluid mechanics. So in general, I want to say that unsteady fluid mechanics is also an important topic in the fluid mechanics study. If we have enough time at the end of this semester, we may discuss or devote a chapter or a session to unsteady fluid mechanics to learn how the unsteady flow problems will be encountered. Going to the next classification, compressible versus incompressible fluid. I underlined fluid. Why? Because there is another slide I'll show you here, and that's flow. So we are discussing about compressible versus incompressible fluid. Incompressible fluid flows assume the fluid have constant density, while incompressible fluid flows density is variable and becomes function of temperature and pressure. So if a fluid is incompressible, like the one you can see here in the left, applying the pressure does not change the volume, and if the volume does not change, then the density will also is the same or constant. So if the density of a fluid is constant, then we name it an incompressible fluid. But as you can see here in the left, where applying the pressure to the surface will decrease the volume, then this means that the density has been increased. So in this case, we say the fluid is compressible. Generally, gases are considered as compressible fluid, and liquids are considered as an incompressible fluid. But there is another definition, which is compressible versus incompressible flow. As you can see here, the flow in which the density of the fluid varies during the flow is called compressible fluid flow. This is generally applicable in gas flow. In case of incompressible fluid flow, the density of the fluid remains constant during the flow. Generally, liquids are treated as incompressible. But there is an exception here, which is very important to consider. If the Mach number, which is, as you can see here, v, or gas velocity, divided by the speed of sound in that gas, is less than 0.3, then the gas flow may be considered as incompressible. By approximation, not exactly, but by approximation. For example, the speed of sound in air is approximately 340 meters per second. 0.3 multiplied by 340 is approximately 100 meters per second. So if the flow velocity, gas velocity, is below 0.3, you can, by an approximation, consider that flow as an incompressible flow, while it's a gas. This is an important thing to consider because it simplifies the flow solution. The next classification is uniform versus non-uniform flow. In uniform flow, if the velocity at a given instant of time is the same in both magnitude and directions, the flow then is said a uniform flow. For example, suppose or consider the flow in a constant diameter pipe where a liquid, it's important to say liquid because if it's a gas, then there may be differences in velocity while the cross-section is the same. We will discuss it later, but for the time being, consider this is a liquid flowing a constant diameter pipe. Then, if the flow is developed or fully developed, what is fully developed? We will discuss about that later in this session. But if the flow is fully developed and there's a liquid and the cross-section is constant, then v or velocity does not change. So rho v over rho x is 0, or we say v constant. In this case, we say this flow as a uniform flow. But when the velocity changes from point to point in a flow at any given instant of time, then the flow is described as non-uniform, like the one shown here. Here, there's a pipe which the cross-section is increasing in the direction of flow. So in this case, rho v over rho x is not equal to 0, and we say this as a non-uniform flow. It may be interesting to know that you can combine different types of flow, or actually there are different combinations of flow in actual world. For example, suppose that we have the same expanding pipe in the last slide. Okay, in this one you have a pipe where the cross section is increasing in the x direction and the flow is steady, but the flow is non-uniform because the velocity will change. So you have a steady non-uniform flow. Now suppose that in the same geometry, the flow is also unsteady. For example, the velocity changes or varies with time. Then you have unsteady flow, non-uniform flow, so you have an unsteady non-uniform flow. Okay, the next classification is dividing the flow problem into 1, 2, or three-dimensional flow. There is another one which we name Axisymetric flow. I'll show you later. In the one-dimensional flow, the flow properties. What are the flow properties? Velocity, density, etc., pressure, acceleration, vary only in one direction, while in the two-dimensional flow, these properties vary in two dimensions. And it's clear that, yes, for the three-dimensional flow, these parameters vary in all the three directions. Actually, in real world, most of flows are three-dimensional. If the flow is three-dimensional, then what's the need to discuss about the one or two-dimensional flow? Can you answer? Yes, because considering the flow as one or two-dimensional will simplify the problem, and it's very important for us to simplify the problems. Another form of coordinates which is generally used for axisymmetric bodies is axisymmetric flow. As you can see here, the flow over an axisymmetric body like the one shown here in the top, or the flow in the bottom, which is the flow in the pipe, generally are considered as axisymmetric flow. In the axisymmetric flow, you have again three dimensions. The one here is shown as Z, or any other name you can say, another coordinate in the R direction, and another coordinate in the theta direction. So please note that this is not exactly a cylindrical coordinate. We'll discuss about that later. Here you can see an example of a two-dimensional flow. For example, if the flow here, as I discussed before, is the flow of a liquid which is fully developed in a cross-section, in a constant cross-section pipe, then it's a one-dimensional flow because it only depends on R or Y, whichever you name. But when the cross-section is increasing like the one shown here, then the flow not only depends on R, for example, but it also depends on X, which is the direction I show here. So this is an example of a two-dimensional flow. It's important to consider or be aware of the results, or what conclusions you'll give, for example, when you consider a flow as a one or two or three dimension. I want to give you an example from aerodynamics, because you know aerodynamics is also an important topic in fluid mechanics. Consider here an aircraft. You can see the distance tip to tip here, as you can see, is named wing span. Okay, and there's a definition in aerodynamics of aircraft which is aspect ratio. Aspect ratio is the division of span to the power of 2 divided by area. Okay, I am showing here two types of aircrafts. The one in the left is a glider with a very high aspect ratio, but the one shown here in the right is an aircraft, a Piper Cherokee, with a low aspect ratio, which is 5.6. What's the relation between this and the topic we are discussing? If you remember, we were discussing about one, two, or three-dimensional flow. I want to say that when solving the flow on the wing of a glider, as I show here, you may consider this as a two-dimensional flow. But when you are solving the problem here on the wing of a Piper Cherokee, then it may be better to consider it as a three-dimensional flow. So in some cases, your engineer conception or perception may help you to select between one, two, or three-dimensional flow. Again, I show here an example of aerodynamic. The green one, or the white ones here, the white streamlines shown here, are the results for two-dimensional flow solution, while the one shown here in blue is the actual flow when you can solve the flow in 3 dimension. And which one is the correct one? Certainly the 3-dimensional one. So it's important to consider different aspects when you want to select if the flow you want to solve may be considered as 1, 2, or 3-dimensional flow. Okay, going to the next classification. The flow may be classified as developed, or as they say, fully developed versus developing flow. Consider the flow which is entering a pipe. This classification, please remember that fully developed or developing flow is only defined for the internal flow. There isn't such a definition for external flow. So this is an example of an internal flow entering a pipe. Suppose that at first the flow velocity everywhere entering the pipe is equal, for example equal to u. When the flow enters the pipe, just starting from the beginning, the flow velocity on the surface will be 0. Why? Because the flow adheres to the surface. We name it no slip condition. No slip condition means that the flow velocity on the surface is equal to the velocity of that surface. If the surface is moving at a velocity, for example v, then the fluid velocity will be also v. If the surface is stationary, like the one shown here, then the flow velocity on the surface will be 0. And this, as you can see, remains the same here, here, here. And the flow velocity on at the surface will be 0. Okay. But the flow velocity in the core, as you can see here, we'll discuss about these terms, Viscid, Inviscid, Irrotational, Rotational later, but this is the core. Okay, for the time being, consider it as a core flow between 2 red lines. The flow in the core region is the same everywhere. As you go further in to the right, you can see that the effect of the boundaries of the pipe will diffuse into the flow, and more and more and more of the fluid will be affected by the presence of the wall. Finally, at a point shown here, point 3, the 2 red lines, which are actually the boundaries between the region where the velocity varies and the region where the velocity does not vary, reach to a point or reach together. Starting from the beginning of the pipe up to point 3, where these 2 boundaries are reaching together, is named entrance region or developing flow. And the flow further on from point 3 to the right is named fully developed flow. As you can see here, and it's very important to learn, is that from the starting of the pipe up to point 3, the flow is non-uniform. Do you remember? Yes. Uniform means that the flow velocity does not change with x. But here, as you can see, the velocity is changing. But from point 3 to the right, the velocity does not change. So, an important conclusion here is that in the fully developed flow, the flow is uniform, while in the developing flow or entrance region, the flow is non-uniform. Okay, coming back here, we discussed about 2 red lines and we named the boundaries. Actually, in fluid mechanics, they are named boundaries, but the name is boundary layer. As you can see here, these red lines are named boundary layer. Do you remember what's boundary layer? Yes, boundary layer is a layer where between the layer and the surface the velocity is changing, but outside the layer, you can see, consider here as outside the boundary layer, the velocity does not change. Okay, what we learned here? We learned that flow in a pipe or internal flow can be divided into developed or fully developed and developing flow. There are some questions maybe in your mind. For example, what is the distance for the developing flow? To what parameters it depends? We will discuss about them later, but for the time being, please note that in the entrance of a pipe or internal flow, there is a length where the flow is developing, and after a specific point, further on, the flow will be developed flow. It may be interesting to know that developing flow is not only at the starting point or beginning of a pipe. It may happen also in the middle of a pipe. For example, consider the flow profile after a pipe elbow, like the one shown here. The green dashed line here is the turbulent flow profile. We'll discuss about turbulent, but this is a normal flow profile, as you can see in the dashed line. Suppose that there is an elbow here, pipe elbow in the left. I've not drawn it, but you can imagine yourself that there's an elbow here. For example, the elbow for this special case is such that the flow is coming from the bottom, and there is an elbow to the right, and you are drawing the velocity profile here. For the case I described, I mean for the flow which is coming from the bottom and then turn to the right, the flow profile, as you can see, is not symmetric anymore. The flow profile is not symmetric anymore. This can also be considered as a developing flow. Why? Because it takes some length for this flow to become again symmetrical, like the one I shown here as a dashed line. As an example, you may consider this. This is the flow coming out of a large tank. Suppose that this is a large tank, or the diameter is large with respect to the pipe diameter. So you may consider the flow velocity here, as you can see, as constant. As I discussed in 2 slides back, it takes some length for the boundary layers to reach, and the distance from here up to here, point 2, is named entrance region or developing flow. Further on, the flow can be considered fully developed. But the interesting point is here. If there is an elbow or any other device which disturbs the flow, then again from here to the left you have the same story. Again, there's a length here from 4 to 5, which is developing flow, and after the flow take its symmetrical form, as you can see here, then the flow can be considered as a fully developed flow. And the story continues. If again there's a disturbation like the elbow shown here, the story will begin. Again you have a developing region and then a fully developed flow. So pay attention to this point. The developing or entrance region does not exist only at the beginning of a pipe or the first section of the pipe. It may happen again and again and again. Why this is important? Because in many cases, for example, this is again a flow meter. I told you that I'll give you a lot of examples for flow measurement because it's an applied topic in fluid mechanics and it's also my expertise. This is an orifice meter. Orifice meter is a flow measurement device where there's a plate here, as you can see, a thin plate you can see here in the flow. passage with a hole in it. The hole diameter is less than the pipe diameter, so when the flow passes through the orifice, then there will be a pressure difference between the right and the left side, as written here or shown here as H, which means high, and L, which means low. Knowing the pressure difference between high and the low side, which is generally measured by a differential pressure transmitter, then you can determine the flow which is passing through the pipe. Okay, what's the relation between this and the developing or fully developed flow? In textbook or references or standards, the discharge coefficient of the orifice flow meter. What is the discharge coefficient? It's a coefficient which you multiply by the theoretical flow equation to determine the actual flow. The discharge coefficient, which is given in the standards, is based on a condition that the flow before, or as we say, upstream of the flow meter, is fully developed. I repeat, the discharge coefficient or coefficient of the flow meter, which is given in the standards, is based on a condition or situation that the flow at the upstream of the flow meter is fully developed. But as I discussed before, when you have an elbow like this, then the flow here is no longer fully developed. It's a developing flow. So if you use the discharge coefficient, which is given in the standards for this installation, then it will give you wrong results. So you can see that this is very important, and this is one of the applications of knowing about developing or fully developed flow. Actually, flow meter manufacturers generally advise the user to install a straight pipe, as you can see here. For example, for this example, it is 10D before this flow meter. Also, there is a distance required downstream of the flow meter. Can you imagine why? We discussed about the upstream effect. The flow direction for this case is from left to right. But why this is required? Can you answer? Why there is a straight length is required after the flow meter? It's an interesting question. Think about that. If don't find the answer, then ask me. This is an example of the advice which is given in the flow meter installation manual. This is taken from a manufacturer. I don't know which type of flow meter or which manufacturer, but what I want you to consider is that, for example, if you have a downsized, you can see here a downsized pipe element here, then for example 15D is required. If you have an upsize, this is required. If you have an elbow here, for example, this is required. If you have dual elbows, for example, this is required. Again, two elbows may be in one plane, the two elbows may be in may not be in one plane, and different upstream length is required. Why these upstream lengths are required? Because the flow should be developed. Okay, it may be interesting for you to know that some flow meters does not require the flow to be developed, or they take an average themselves of the flow. We may discuss about that later if I remember. Okay, going to the next classification. The next classification is viscous versus inviscid flow region. The flow may be classified into inviscid and viscous. Inviscid flow, you can see here, is considered as a flow region where the velocity does not change. But in the viscous region, as you can see here, in this picture may be better to start. For example, this is again the flow entering a pipe, the entrance region or developing flow, and from here to the right we name it fully developed flow. As you can see here, in the core region, okay, do you remember the core region, the yellow one shown here? In the core region, the flow velocity is equal. You can see here, This is equal to this, to this, to this. This is not equal to the left one. What's the reason? Think about that also. We'll discuss about that. If you don't find the answer, again ask me why there's a difference between the flow velocity here, and maybe here, but from this point to the right the velocity does not change. Okay, come back to the question here. The flow velocity in the r direction here, as you can see, is not different. See, the flow in this region where the velocity is constant in the r direction is called inviscid region, while the flow in the boundary layer where the effect of the wall dominates, because why the velocity is changing here? Because of the effect of wall and the viscosity, is called viscous region. The same applies here. This is the boundary layer around an airfoil. Here there is another definition instead of boundary layer. We'll discuss about later, but consider this as a boundary layer around an airfoil. The flow within the boundary layer where the viscous effects dominates is the viscous region, and the flow outside the boundary layer is called inviscid region. What is the reason for classifying the flow into inviscid and viscous region? Because, as you can see later in the course, the governing equations of fluid flow for the inviscid region are much more simpler than the viscous region. So you may divide the flow into inviscid and viscous region and apply different governing equations for these two regions. One set of equations for the inviscid and the other sets of equations for the viscous region. Why? Because it again simplifies the solution or decreases the computing time required to compute the flow around the body. I shown here the viscous and inviscid region on the airfoil shown in the previous slide, here in more detail. Consider this as a surface. The surface may be an airfoil or a flat plate or any other thing. As I discussed before, the velocity at the surface is 0. What was the name of this condition? Yes, it was no slip condition. But far from the surface, in the y direction, as you can see, the flow velocity will be increasing. Up to where? The flow velocity will be increased up to the point where it reaches to the velocity of outer layer, or free stream velocity as they say. The region of the flow below this point is considered as viscous region, while the flow above this line is called inviscid region. So again, as you can see, in the viscous region you have the velocity gradient, but outside the viscous region, which is inviscid region, the velocity gradient is 0. What is velocity gradient? Velocity gradient is du over dy. Du over dy. You can see here that du over dy varies here, but from this point further on here, rho u or du over dy is 0. What's the meaning? The meaning is that u does not change with y. But here, when du over dy is not 0, it means that the velocity is changing with y. Here you can see another example of viscid versus inviscid regions of flow. For example, when you consider the flow over a cylinder, like here shown here in the left side, as inviscid flow, there is no separation at the back side of the cylinder. This is not a real flow actually. In the real world, there's a separation point. What's the meaning of separation? The point at which the flow separates from the wall. We'll discuss about that more in detail later. And there will be a wake region is produced here. This is a viscous flow consideration, while this is a inviscid flow consideration. From this simple picture, you can understand that it seems that in some regions of the flow, you may consider the flow as inviscid, but in some regions of the flow, it may not be considered as inviscid. You may remember that what's the reason for considering the flow as inviscid. Do you remember? Yes, the reason was to simplify the flow solution. Also, there may be some geometries where consideration of the flow as inviscid may give you adequate or reasonable results, but there may be some geometries where considering the flow as inviscid may give you wrong results. Can you imagine what type of geometries can lend themselves into the inviscid flow solution? Can you give me, for example, some, or imagine some geometries that may be solved by inviscid flow assumption, and some geometries that generally give you wrong answer if you consider them as inviscid flow? Think about that and answer yourself. If you didn't find the answer, then ask me. Next classification is rotational versus irrotational flow. Rotational flow means that the fluid particles, while flowing, also rotate about their own axis, like the one shown here in the bottom left. See this? This is the rotational flow. The fluid particles, while flowing, also rotates about their own axis. But in the irrotational flow, the fluid particles do not rotate about their own axis while flowing. There may be distortions, but the flow is irrotational. In the kinematic of fluid, we will discuss more in detail about irrotational and rotational and how to determine if a flow is rotational or irrotational. We will discuss about that more in detail. Next one is the classification of flow into ideal versus real flow. Real fluid flow implies friction effects. Ideal flow is a hypothetical flow which is not real, and in that flow we neglect viscosity effect or neglect friction effects, or there is no friction. As an example, consider the flow in a pipe. In real world, as we discussed in previous slides, the flow velocity at the surface is zero. What was the name? No slip condition. But in ideal flow, as you can see, there is a slip condition instead of no slip condition at the wall. Is it real? No. Is it not? It's not real. Can we use it? In some special cases, by some approximation, you may use the ideal flow solution instead of real flow solution. What's the reason to solve for a flow which will not give you right results? Because of simplification. But please note that simplify the problem, not more than required. Actually, if we want to define ideal flow, an ideal flow is the combination of inviscid fluid. You may remember that we discussed about this. Inviscid fluid means that the fluid viscosity is zero. Is there a fluid in the world that the viscosity is zero? No. It's an assumption for the low viscosity fluids. And if you have a combination of inviscid and incompressible flow, do you remember incompressible flow? Yes, that was a flow where the density does not change with time or any other parameter. And if you combine them together, then you have an ideal fluid flow. Okay, there is some definitions here which is very important. For example, this last one, do not confuse ideal fluid with a perfect gas. Perfect gas is another definition, or ideal gas, and ideal fluid is another definition. Okay, and this is also important. Let's review it. Practical applications. What is the practical application for ideal flow? Many flows approximate frictionless flow where away from the solid boundaries, because at At the near the solid boundaries is the region where the viscosity effects are dominant. Far from the boundaries, generally you may neglect the effects of viscosity. Okay, the next classification is laminar versus turbulent flow. In laminar type of fluid flow, particles move along well-defined paths or streamlines. The fluid layers move smoothly over the adjacent layer. The fluid particle moves in a definite path and the paths do not cross each other like the one shown here. But in turbulent flow, fluid particles move in a random and zigzag way. Turbulence is characterized by formation of eddies, as we say. So, the flow can be classified into laminar and turbulent. But an important distinction should be made here between internal and external flow. Let's start with the internal flow. For the internal flow, Reynolds was the one who made an experiment to show the effect of a flow of being laminar or turbulent. There's a flow in a glass pipe here where an ink is, a colored ink is injected into the pipe, as you can see, or a dye, as you can see here. This is the pipe, a glass pipe, and this is a dye streak which is injected into the pipe. The flow of the pipe can be varied, for example, by a valve or something like this. So you can increase the flow velocity within the pipe. Reynolds noticed that when the flow velocity is less than a certain amount, the ink is moving exactly in a straight way. Passing from a specific speed and above, the ink will take the form like the one shown here. And if you increase the velocity again and again, then finally the ink will be disturbed in the flow, as you can see here. Reynolds made the experiment with changing different parameters in addition to the velocity, and then he noticed that this type of flow phenomena, which you can see here, is dependent not only on the velocity in the pipe, within the pipe, but also on the density, viscosity, and diameter of the pipe. He put all the parameters in one dimensionless parameter, which is named Reynolds number. Please note that we are discussing or starting from internal flow. Do you remember? The definition for the external flow is somewhat different, as you can see here. Okay, for the internal flow, Reynolds number is defined as V multiplied by D over nu, or you can say it V d rho over mu. You know that mu is actually the dynamic viscosity or absolute viscosity, and if you divide mu to rho, then the result is named kinematic viscosity. You can see that in the unit of kinematic viscosity you have no sign of force or mass, but in the dynamic viscosity you can see here Newton, which is a sign of force. So in internal flow, Reynolds number can be written either based on absolute dynamic viscosity or dynamic viscosity, or based on kinematic viscosity. For the external flow, Reynolds number is defined as rho multiplied by V multiplied by X over mu, or based on kinematic viscosity, again you can write this. There is an important difference between these two, or actually two important differences. The first is that here V is the average pipe velocity. It's not written here, but please note that V here is the average velocity within the pipe, because you remember that the velocity in the pipe is not the same everywhere. It varies from 0 at the wall to the maximum velocity at the center line if the flow is fully developed. Here you have V, which in this case V is free stream velocity. So for external flow, V is free stream velocity, or the velocity far from the surface, and for the internal flow, which V is average velocity in the pipe or channel or something like this. The next difference is about the dimension, the D here and X here. In the internal flow, D is the pipe diameter, or if it is not a circular cross-section, you have the hydraulic diameter. But in the external flow, as you can see here, X is the distance from the leading edge. X is the distance from the leading edge. An important conclusion which may be taken here is that if the pipe cross-section is constant and V is constant within the pipe and D is also constant, as nu is constant, then the Reynolds number in the pipe will be constant. It will vary either if V or D or nu varies, but if none of them changing, then Reynolds number will be the same. But here in the external flow, as X is different at any location, then the Reynolds number here, for example, here or here, will be certainly different, unlike the one we discussed here about the internal flow. This is a very important thing to consider. What are the criteria for the flow to be laminar or turbulent? The criteria for the external flow is Reynolds number with the definition I told before. You remember, U infinity is the free stream velocity, to be more than 500,000, and for the internal flow, where UM is the average velocity or mean velocity in the pipe, is for the Reynolds number to be more or less than 2,300. There's a transition region also, but for the sake of simplicity, we neglect it, and in this course, flows, internal flows with the Reynolds number below 2,300 are considered as laminar, and for external flow, flows with the Reynolds number below 500,000 are considered as laminar flow. As you can see here, there's a transition region, for example, for the external flow. This is, for example, a flat plate or an airfoil or anything else. You can see that there's a free stream far from the surface. When it reaches to the surface, again, because of the no slip condition, the velocity at the surface will be zero. It will gradually increase, as you can see here, and up to what point? Up to the boundary layer, which is this line or this curve. Above the boundary layer, the velocity is not changing, but below the boundary layer, where the flow is viscous, the velocity is changing. As you can see, there is a transition region between laminar and turbulent flow, but for the sake of simplicity in this course, we take the critical Reynolds number as the one shown in the previous slides. There is an exercise for you here. What do you think? Which profile has larger wall shear stress, laminar or turbulent? The one shown here in the left is a laminar flow profile over a flat plate, and the one shown here in the right is a turbulent flow profile. Please answer referring to the below equation. What is this equation? This is the Newton law of viscosity. Tau, or shear stress at the wall, is mu multiplied by round u over round y at y equals 0. What the meaning of y equals 0? It means at the surface. Red dashed lines are tangent to the velocity profile at y equals 0. These red lines are tangent to the velocity profile at y equals 0. Okay, can you answer this question? Which profile has larger wall shear stress? You can see that, considering mu as constant, the only parameter which may help you to answer this question is to determine if rho u over rho y at y equals 0 is larger or smaller. What do you think? Is it larger in the right picture or in the left picture? Rho u over rho y at y equals 0. Which one is larger? You can stop the video and if needed repeat the video to listen to my question again and try to answer this question. Which profile has larger wall shear stress? Referring to this equation, I do not want you to answer this question just by imagination or something like this. I want you to answer the question referring to this equation. Okay, I hope you answered the question. Actually, this shows better my question. I forgot to click on it. Actually, the question is which angle. By which angle I mean the red angle or green angle. Which one is the angle which you use to determine rho u over rho y at y equals 0. Okay, let's see the answer. The angle shown in the picture in red shall be considered for determining du by dy. Why not this angle? Because, as you can see, it is rho u over rho y, and u is on the horizontal axis and y is on the vertical axis. So, rho u over rho y is the gradient which is shown here by red, not the one which is here. And simply you can see that in the turbulent flow, rho u over rho y at y equals 0 is much more. So wall shear stress is larger at turbulent flow. There are some exceptions and we'll discuss about them later in the course. The same you can see here for the velocity profile of laminar and turbulent flow in a pipe. Here I show the flow profile in a pipe in laminar and turbulent flow. For the laminar one, you can see here that the type is a parabolic shape, but in the turbulent flow it is somewhat flattened. Can you see? Again, I ask the same question. In which one the wall shear stress, referring to the equation, the Newton equation, is larger? Think about that, and if you have a still problem for answering the question, refer to the previous slide, and this is very important, I think. Okay, the next classification is classifying the flow into a steady and unsteady flow. You can see here a picture showing the laminar and turbulent flow. The problem here is that laminar flows may be steady, as you can see here, but turbulent flows, as you can see here, are always unsteady because there are a small perturbation around an average velocity, which we name them u prime, which are added to the average velocity. It says here that laminar or turbulent flows both can be steady, like the one shown here, or they may be unsteady, like the one shown here in the bottom. But if the flow is steady in the turbulent flow, you should consider in your mind, in back mind, that this type of flow, I mean turbulent, is actually a turbulent flow, but I may consider a mean velocity where the mean velocity does not change with time. So in the laminar flow definition, in the laminar steady flow, we say that the velocity does not or does change with time. If it does change with time, then the flow is unsteady. If the flow velocity does not change with time, it is a steady. It's a steady laminar flow. But for the turbulent flow, you should say that if the mean velocity is changing with time, then the flow is a turbulent, unsteady flow. But if the mean velocity does not change with time, then this is a turbulent, steady flow. Okay, the next classification is the Newtonian versus non-Newtonian fluids. You may remember that there is a relation between stress, shear stress, and shear rate. And that's the Newton law. You can see here the drawing for three fluids: oil, water, and air. As you can see here, the viscosity of Newtonian fluids, as we name them, will remain a constant no matter how fast they are forced to flow through a pipe or channel. It means that viscosity is independent of the rate of shear, okay, or rate of deformation. So, in this case, if you plot a stress versus shear rate or rate of deformation, then for the Newtonian fluid, a straight line will be given, derived, okay, where the slope of the line, as you can see here, which is shear stress here in the denominator, over shear rate or rate of deformation du dy over dy, which is that the denominator is the slope of the curve. So if you compare, for example, air with water with oil, the graph for the oil have a higher slope, so the viscosity is higher, while for the air it has a very generous slope and the viscosity is lower. But for the non-Newtonian flow, as you can see here at the right, the shear stress does not have a constant relation with the shear rate. The interesting point here is that there are different types of non-Newtonian fluids. Bingham plastics, as you can see here, are fluids that require a minimum stress to be applied before they flow, and that is the minimum stress. You can see that this stress should be applied for the Bingham plastic to start deforming. These are strictly non-Newtonian, but the interesting point here is that once the flow starts, they behave essentially as a Newtonian fluid. As you can see here, the relation is linear. Okay? A great example of this kind of behavior is minus. For non-Newtonian fluids, viscosity is dependent on the shear rate. It may be shear thinning or shear thickening, as you can see here. This is the line for the Newtonian fluid. These are the line for the non-Newtonian fluids, okay? And there are a lot of examples. I refer you to this website. It's a very interesting website which with a lot of interesting discussion about the non-Newtonian fluids. Have a look at that website. Okay, I think these are the next classifications. I hope you are not tired. The next classification is separated with versus attached flow. Consider the flow over a surface, over a curved surface like the one I shown here. At point A, the flow is attached flow. At point B, again, the flow is attached. And as you can see, du over dy, u is the velocity, y, suppose that y is normal to the surface, is more than 0. It means that when y is increased, u will be also increased. An important point here is to consider is that when you move to the right, du over dy is decreasing. If this happens, then finally at a point shown here, du over dy will be 0. This is the point where separation or flow separation will be started. Further on to the right, the flow is named detached flow because it is detached from the surface. In the detached flow, as you can see, d over dy is less than 0. What does it mean? It means that when you move far away from the surface, the flow will be decreased, the velocity will be decreased. But what's the reason behind a flow to move toward separation? Why this type of flow shown here in this slide is interested to be separated from the flow? The reason is in the next slide. In each region of the flow, the pressure gradient means rond P over rond X, or pressure with respect to X, is either negative or positive. If the pressure gradient is negative, we say it's a favorable pressure gradient. But if the rond P over rond X is more than 0, or P increases along the surface, then we say that there is an adverse pressure gradient. So if the pressure decreases along the flow, it's a favorable pressure gradient, and if the pressure increases along the flow, then flow path then it's an adverse pressure gradient. The condition for the flow to be separated from the surface is that there should be an adverse pressure gradient in the flow. If there is a favorable pressure gradient, generally separation does not happen. But if pressure gradient is more than 0, or there is an adverse pressure gradient in the flow, then the flow may be separated from the surface. Maybe, For example, suppose that there's a curved surface like the one shown here. There's a flow from the left to the right, and this is the point where from this point on to the right, the pressure gradient is adverse or more than 0. When the pressure gradient is adverse or more than 0, then as you can see, the velocity gradient at the surface, rond u over rond y, will be gradually decreased. At a point like the one shown in the previous slide, which is the point of starting separation here, where d over dy is 0, separation starts. From this point to the right, as you can see, you have flow reversal. And when you have flow reversal, you have vortices near the surface, and the region here where vortices exist is named wake region. This is an important topic in fluid mechanics, and we'll discuss more about that later. You can see here some examples of attached and detached flow. Attached versus detached. When separation occurs, we say that the flow is detached from the surface. For example, here an airfoil is shown at a low angle of attack. Angle of attack is the angle between the far stream velocity, or the velocity which is coming here, between the flow far stream velocity line and the line which is connecting the leading and trailing edge of the airfoil. You can see here the same airfoil at a larger angle of attack, and as you can see, where the angle of attack is increased, then there may be separation at the back side or upper side of the airfoil. If the angle is increased more than a critical angle, which is shown here, the lift of the airfoil which will be suddenly decreased, and we name this as stall of the airfoil. We may find to discuss about this later. I want just to show you here the attached versus detached flow. You can see here again some examples. For example, for the flow over a cylinder, when the flow is laminar and Reynolds number is, for example, less than 1, the flow is attached to the surface. Increasing the flow, you can see that there are vortex produced here, and the vortex will be increased. the vortex will be shed from the surface, and finally there may be a wake region behind the surface. Starting from this picture, there's a separation of the flow. Okay, the next classification is to classify the flow into single or multi-phase flow. You know that these are three forms that we are discussing about: gas, liquids, and solid. These are single phase systems. Actually, we are not discussing about solids, but when it comes to the multi-phase flow, we may have solids, because you may have different combination of these three systems. For example, you may have a combination of gas liquid, you may have a combination of liquid solid, you may have a combination of gas solid. For example, where you may have a gas solid combination, for example, in a cement factory, where for example gas laden solids are for example cement particles are in the gas flow, for example. Analyzing these type of flows is outside the scope of this course. You may have a course later under the name of multi-phase flow, and it's also a very interesting topic in fluid mechanics. So, summarizing what we said up to now, the flow may be classified into different forms depending on fluid properties, like incompressible versus compressible fluid, or depending on the flow properties, like laminar versus turbulent flow. If you remember what I discussed, then you may name others. If you don't remember, please listen the video from the beginning. And this is the end of part 1. We'll discuss about other topics later. Thank you and take care.